Let me. Okay. Well, hopefully you guys can listen to me. If something doesn't come across due to the internet, just ask me to repeat myself. I'm remote and all those kinds of things. So it is an honor to be here. I saw the people connected, and I just want to say hi to a lot of friends. I really miss the real workshop, so we will just have coffee with each other and actually, really like discuss in person. But of course, please use it. I'll be in the Slack and stuff to answer questions as well. So I really just want to hark back. I mean, the presentation of Frank was amazing because he gave us a huge overview of the field, and I just want to say have a typo actually. Anyway, I just wanted to share with you, where we started. It's amazing that it's been 16 years ago, but I was a postdoc back then with Martin Head Gordon and Tommy Dutoy, Peter Lowe, and myself. Literally just took what Frank was talking about, the quantum phase estimation algorithm, and applied it to chemistry. And at that time, what we did is just map using the Jordan-Wigner, the molecular Hamiltonian, to the spin Hamiltonian, and just show numerically that you can do this with a small basis set molecule. And wrote a code called Tequila to do that. I'll come back to that later. And show this plot, right? And this plot has been shown many, many times. What is important to us, and this is just a reminder, that's what I'm showing you this slide, is that one of the attractive things of chemistry is that even if you use what could potentially even be wasteful, a mapping of 2 qubits per spin orbital, molecules as complex as cholesterol will take thousands of qubits, and molecules that potentially could be intractable will take hundreds of qubits, right? So, but by that, what do we mean by that? We mean, of course, molecules for which you want to get an exact solution within a basis. And that discussion is a long discussion because you might not need an exact solution within a basis for an application. You might need it. You might need it to calibrate machine learning methods. So the quantum computer perspective of when to use it is also quite nuanced, and of course we can go into that in the Q&A. So, of course, the era that we're on right now is the NISQ era. So the algorithm that I showed you before was, requires a lot of gates, and of course now there has been incredible work by many people in the room. For example, the Microsoft group, the Google group, our group as well, and many other groups have lowered the cost of the coherent algorithms. And that's a topic by itself, how in the long term you could use a quantum chemistry algorithm for the long term, and how will those look like? Okay, you will need to use these very sophisticated algorithms that reduce the asymptotic cost, but of course that comes at the cost of many, many qubits in the near term, and many, many gates in the near term. And therefore, what you really want to think about more than that is NISQ computers at the moment. And this is just a little picture. Frank already gave us a picture of it. It's a specialized audience. The only thing I'm gonna just talk about is the fact that chemistry as optimization as well as machine learning in papers such as this is pointed as one of the near-term applications. Which one exactly is going to be for what application? This is going to be a very, very fast-moving target, and to me, it doesn't really matter. I think when we need to get to this quantum advantage, we'll be figuring out what's the best application that goes into somewhere useful. This is a good moment for me to state the position of Zapata Computing, the startup that was already mentioned. And I like that position about when we will get advantage with an NISQ computer. Let's just think about it as placed in any location, anywhere in the production of a company, for any reason. Okay, so if you use a quantum computer in any situation, in a real application for industrial purposes, or for some company that is really using it for it, that would be the point where we think a NISQ computer is useful. So rather than a theoretical approach or thinking about energy costs or whatever is going to be your metric, I think that's a very simple way of thinking about when we're going to be able to do this. I think it's possible that it's going to happen in the next few years if we continue the lowering of the cost of the algorithms and the increase of the power of the near-term quantum computers. When exactly, we don't know. In terms of review, I saw that Sam McArdle here, first author and main pusher of these reviews of modern physics, basically review I participated lightly on quantum computational chemistry. My research group, many of the people here are now at Zapata Computing. wrote this review on ChemRep around the same time, also on quantum chemistry for quantum computing. So I recommend you to read those two, and of course there's many other reviews out there. One recent by Garnet Chan, for example. Here is one that we just put out, and the reason we put it out is because my group really couldn't keep up with the amount of NIST papers that were coming out. So I just want to show you some screenshots from it and invite you, because at the moment we're revising it to send it to the journal, and therefore we're still in time for getting your suggestions of things we missed or corrections. I mean, we're of course impossible to look at all the possible variational algorithms in detail. And here you can see some examples of variational algorithms that we already have discussed. What they share in common is they minimize or maximize some objective function. They usually vary the parameters of a quantum circuit, and they push to the classical computer most of the computation, and the quantum computer becomes a state preparation and measurement device. So these are some examples from my group and others. But what I want to show you is, for example, just in many body, which is, I guess the topic of this talk is chemistry, but I started a little bit broader, following up on Frank. I really am humbled by looking at all the different algorithms. For example, Guillaume Vernon's thermal state preparation, or many algorithms related to the quantum autoencoder that I mentioned before, or of course the family of VQE algorithms is growing extremely fast. And I will really apologize in advance to all the audience that is doing VQE development. I will mention just a few developments using examples from my group and others, but of course I won't be able to cover the entire VQE field. For example, here we have machine learning applications and optimization applications. And I like this a lot because I think this is what we really need to think about more and more. Others, okay? So linear algebra will become potentially an interesting direction that still can be exploited. And finance seems to be growing, and I wouldn't really discount it, okay? Because if you find a clear application like say Bitcoin is, an application of that type, maybe that's what's going to dominate what quantum computers are used for in the near term, right? So this is really a moving target, and I would like you to see also. I'm going to just page through. Look at the years of publication of all the algorithms we're showing here. It is really an exponential growth, and therefore we want to make this review live. It's going to have a website that's going to be updated continuously to be able to try to come up with a review that doesn't die after 2 years. Okay, so just briefly, what is a variational quantum algorithm? Again, you will prepare a wave function, and a lot of the work that is happening in my lab is what is exactly the wave function that you need to prepare. It could be absorbed. It could be absorbed here in the unitary. You could also think about what is the best measurement scheme, and that's a huge area that I will just touch on. And then, of course, big concern due to the Barren-Plateau's results of Jared McLean and collaborators. What is going to be your optimization strategy? Okay, because obviously we know now results that if you have a very deep circuit, as you increase the depth of the circuit, if you know nothing about your state or ansatz, that you're just optimizing blindly, you might fall into a regime that you're going to not be able to optimize, because in general the gradient expectation values will vanish. So let's just go into details about the VQE. Again, my perspective again is biased, and I'm happy to, of course, discuss with everybody in the Slack and in the chat or whatever. So it was funny when Jared was suggesting the name QPU originally. It sounded like a weird idea, but now everybody thinks, and I think that quantum computer is really like a GPU. It's always going to be surrounded by huge amounts of classical computation. Even the error correction regime, the classical computation costs could be incredible just to be able to run a quantum computer. So as Frank was saying, really don't underestimate the power of the classical computer to really squeeze the lime juice out of a quantum computer. Very precious object. So let's just talk about all the things that go under the hood, and I think I'll show you examples of improvements in many of these, if not all of these, as I go along. But if you want to map a many-body problem, or in particular a molecule, to a quantum computer, you will need to take its fermionic generators. The problem is fermionic. map them to circuits that eventually need to be mapped to public strings, of course, to a particular hardware or a particular abstract simulator that you want to look at with noise or without noise. And then you want to perform a classical algorithm for the variational optimization. Okay, so that's going to be the cycle that you're going to be thinking about. And more you will see there's going to be more and more integration of fast computing, as IBM is suggesting, and many others, as well as Google. Really, really fast computation. It could even be FPGAs close to the quantum computer, because this cycle really needs to be done fast, and the computation might not be trivial. So what are some of the things that are going on in the field? Okay, and I mean, I'm just listing a few groups here. I could fill the slide with names here. People are very actively developing excited state methods. I will just in the next slide mention a little bit about the reduction of measurements work by my colleague Artur Ismailov, Google, and others. A lot of thought has going on in what is going to be the right ansatz. Big hat tip to Nick Mayhall and for introducing the adaptive VQE, for which my group has done variants and many others that allow you to actually really start selecting terms smartly and build your ansatz on the fly. And the new family of universal unitary coupled cluster methods, it's another big area. And of course, how to optimize to avoid barren plateaus. I think these are, in my opinion, some of the 6 directions that people are going through, but there must be 7, 8, and 9, okay? But if you want to know where the state of the art is, you might want to go to our review or others and start looking at these different type of directions. So just to example, this is a slide I stole from my collaborator and friend, colleague, Artur Ismailov, which, I was very lucky to move to Toronto and find out he was starting to work on quantum computing just across the hall. And it's really a pleasure because he always comes to my office with a new discovery he has with his group. It's super exciting. And, he's been thinking a lot about the algebras of the measurements and how to think about how to group measurements. Because, for example, if you can, for example, parallelize over measurements. If you measure some things that are uncorrelated, you could also continue by saying, what was the wave function that was projected out? Which further measurements can I do to it to not completely prepare the state from scratch? And so on. And with all of those tricks, you get a scaling in the number of measurements that now is going low powers of 1, like 1 to the 0.4, right? Which basically means you're lowering the number of measurements required, which has been one of the biggest criticisms of the variational quantum eigensolver, both in the scaling, but also in the prefactor. So now I want to tell you a little bit about the code Tequila, because Tequila has revolutionized what's happening in my lab. And it's just an example of one of these modern codes, such as Penny Lane and others, that exploit really like the machine learning frameworks that have been developed over the years, but now for quantum computing, and allow us to do really rapid algorithm prototyping. And here are some of the authors. I saw that Matthias is online. And I really apologize, I forgot. I did the screenshot this morning. I didn't realize I cut off some of the authors, so I should have clicked on show author list. I just wanted to show them here in the accepted manuscript. So again, it's funny because we started with a code called Tequila, but then when Jacob wrote this new code with all these other people like Sumner, we wrote it again and we named it Tequila again. So the reason I'm advertising Tequila, so to speak, is because it's a quite simple code for you to do prototypes. What Jacob wanted to do is have an algorithm development platform where whatever you write in the blackboard really takes very few lines to be implemented. Okay, in this particular case, here is the beryllium hydride molecule in the 631G basis, and you can see literally pretty much the code that will allow you to get the molecule energy. And why is it so simple? It is because it is standing on the shoulders of giants. Penny Lane also introduced recently support for JAX. I really don't want to underemphasize how important are tools like JAX, which are very simple automatic differentiation tools in Python. And we stand, of course, in Google's Open Fermion, and of course, the quantum chemistry packages like PyACF and Psi4, and the simulators, okay? So what is really cool about Tequila is that you can write an interesting expectation value that you want to minimize, for example, the Hamiltonian square. And just by using the chain rule and automatic differentiation, the code will actually reduce that to the right primitives without you not worrying about if you want to optimize the log of the wave function to the 3 halves or whatever weird expectation value of the energy to the 3 halves, whatever expectation value you might want to minimize for excited states or ground states or whatever. You just need to write it in algebra, and then the code will actually figure out what is the actual gradient. And that's very important, because then if you couple it to the quantum chemistry packages, then building the wave functions, and all of these functions are very useful to actually test new ansatz, allow you to actually optimize molecules. So I really invite you people to actually use it, help us. Something that will be very useful is we can help you implement your algorithms in small few subroutines in Tequila to make it, we hope, kind of a gathering ground for all the community to be able to compare methods with each other. That was the original idea of the algorithm. So let me show you that something that we did with Tequila. It just appeared in JPC LED this year. That basically highlights, I think, very importantly, what is what I think a lot of the action will be in the next few years, and it's really squeezing the amount of power of the classical computer. So people usually started thinking, well, including us and everybody, okay, let's use just unoptimized orbitals and do the quantum chemistry in the basis sets that we know and love, right? And of course that makes sense, because that's what the quantum chemists have been using. What I think you have to rethink things and think about, well, if I'm going to do a quantum computer, I might as well spend as much computing power as I can to actually build the most sophisticated basis set I can, okay? And this is where we use correlated surrogate model. In this particular case, a second-order perturbation theory based on the very elegant Madness code, which is a multi-resolution code that has a very, very sophisticated real space basis developed by Harrison and coworkers. Jacob used to be a co-author of that code. And this adaptive basis set, of course, we believe is going to be a very tractable and optimal representation for a particular given molecule. So rather than going the traditional basis set approach, which will just fix it at the beginning with unoptimized things that we will do in quantum chemistry, because in quantum chemistry, other aspects are cheap, like just classical computing in a supercomputer, then takes the PNOs, or pair natural orbitals, that come out of this multi-resolution analysis, and builds a qubit Hamiltonian where you can apply all your previous tricks. Okay, you could apply adaptive methods. You could apply your particular optimization algorithm, particular ansatz, or even gradient algorithm, as I'll mention the gradients in a second. Okay, so this basically tells you that now you are in a situation where I recommend that everybody does this before. Okay, you're going to really do a benchmark. Okay, because now you just run your variational algorithm, and the gains are huge. Okay, so you can see here, for example, the energy of the hydrogen molecule. I'll be using it as a particular kind of like hobby horse for this. But you can see here the exact solution. This will require 120 qubits. Okay, and you can see that with multi-resolution analysis, you're approaching that particular energy with only 4, as compared to the unoptimized orbitals. So why would you want to do this? Because if in the paper we spend some time really using large quantum chemistry calculations to estimate what will be the number of qubits that you will require to do something in the Gaussian basis set limit. Okay, here is 56 qubits, 20 to 56 qubits. You could do it with 8 here, and 300 qubits. You could do it with 20. So this is one of the examples where things make me very optimistic, because the classical computing side can be exploited to lower the costs, while the the experimentalists keep working and increasing coherence and having more and more intermediate scale quantum computing error correction techniques. So another example from our own lab was the idea of combining knowledge from DMRG, for example, to actually think about what is the best way to build a smart unitary coupled cluster algorithm, right? An algorithm where we do not use all the entanglers, but we use entanglers that are based on mutual information based on a classical computation. And this classical computation can be quite cheap. You could obtain this from a very, very low bond order of DMRG calculation. It already gives you some idea of what are the important entanglements that you want to keep in your ansatz. Okay, so you could do it more in a blind way, or you could do it informed by classical quantum chemistry methods. And again, as I mentioned before, these can be readily combined with the previous algorithm I showed you before. Another example from my lab that I really want to highlight, because it will tell us about, I think, where also the future is going to be, is going to be in the melding or in the combination of variational eigensolver algorithms with machine learning algorithms. Okay, so obviously there is a lot of work that we could discuss by many groups on classical machine learning outside of the variational eigensolver. But here what I'm really talking about is the quantum machine learning approaches basically combined together with variational eigensolver. This is work spearheaded by Alba Cervera Lierta in my lab. And what Alba and others were looking at is the idea that maybe what we want to think about when we have Hamiltonians that depend on a particular parameter, lambda. And this particular parameter, lambda, could be a 1 or 2-dimensional potential energy surface. It could be an external magnetic field for a many-body system. Are the wave functions related? And if they are related, can a shallow machine learning wave function with a proper encoding combined with perhaps, multiple measurements over different values of lambda, provide us, instead of just one wave function, the family of wave functions as a function of this parameter lambda, in other words, the thetas as a function of lambda, okay? And again, here, therefore, this encoder will actually allow us to try to come up with that, and hopefully it is a shallow circuit, okay? And this is what we like to call the meta-variational quantum eigensolver. The field moves so fast, and actually one of the real motivators of us writing the review is that when we already had the paper submitted to the journal in the archive, Keisuke Fuji wrote to us and says, look, we have a very, very similar idea already published in PRA applied. So we were like, wow, oh, sorry. So these are just kind of like very similar approaches. Okay, so I really want to give them credit for the original idea. We call this meta VQE. And again, the way we explain it at least is by allowing to have this mixed layer, we optimize the expectation value of the first of all, you're going to just test it, you will just run the encoding and etc. But you could also, once you have your encoding, go and do another round of VQE, which will actually now optimize further, and we call that the optimized meta-variational quantum eigensolver. And the way I think about it is maybe your encoding was not completely correct. Once you optimize it for the family of states, and you want to further optimize each state again, okay? And sometimes if you do that, for example, this optimized meta-VQE, this is the traditional hydrogen 4-molecule square, okay, that gets harder when it's a true square before you start stretching it. And you can see that when you actually do the opt nonlinear meta-VQE, kind of the best state of the art, you will actually take advantage of that particular new variation of freedom of the encoding layer to actually outperform and gain over the errors of traditional VQE or meta VQE, okay, or etc. Okay, so you can see here that the meta VQE, which is not optimized, suffers obviously at this particular region of the wave function that is hard. So you could imagine that many body system, obviously, when you go close near to a phase transition, meta VQE will not really know what to do very well. But anyway, but I believe meta VQE will be a tool in the arsenal of people that want to start thinking about, again, wave functions as a function of changing parameters in many body physics and chemistry. Another potential highlight that was just accepted in chemical science from my group, this is basically an idea of Jacob and worked very hard with Abhinav, is thinking about why, the traditional gradient of a fermion operator written in terms of spin operators will in general require order 2 to the 2 to the n measurements using the traditional shift rule that is now implemented in many packages, okay, such as Penny. So this is where I think the power of really thinking about the problem at hand comes. Turns out that Jacob thought about the fact that the reason you can get the derivatives of the spin operators is because you have only 2 eigenvalues. So is it possible to project out for the fermionic operators the subspace, so you also only have 2 eigenvalues that you want to care about, so you can do the same type of 2-point, or in this particular case 4-point to be exact, measurements, okay, rather than these 2 to the 2 to the n that come from decomposing the fermionic operator into the spin operators. And turns out this is possible. I'm going to leave you to the details for the paper. But I want to show you how these two parts that are defined there, okay, this G plus and G minus, when you get their gradients, obviously the gradients are not the total gradient, but compared to this exact fermionic gradient here in black, okay, either an exact fermionic differentiation will be exactly on top of it. This is this fermionic shift operator, or even an approximation, okay, that thinks it's a real operator for molecules seems to be doing really well. And obviously, if you are thinking about derivatives, you might just want to think about where the derivative vanishes. Its value might not matter as much, depending on your optimizer. Obviously, it's better to be exact. So, but you can actually see that for this minimal basis for orbital hydrogen example, really you don't lose anything by using these new operators. You need to use some gates to build those projectors that you need to add to your cost. But we think they are negligible to the cost of a unitary coupled cluster circuit in general. So this is another black box that I recommend to combine. So a good picture that you want to have in your mind is that I've been introducing to you work from my group, but many other groups are doing the same. Work that looks like puzzles of a jigsaw that you can mix and match. And this is why codes like Tequila are quite important, because they will allow you to put things together in a rapid development fashion. So I think what's going to happen in this community is that given that the tools are becoming easier and easier to develop, and given that these jigsaw puzzles are coming up in a rapid pace, we're going to see an explosion of creativity from the community that will be hard to stop. Okay, so I am at 26 minutes. I am assuming the 45 minutes I have are with questions as well, right? So I'm going to do a time check here. Is that correct, right?
Yes, that's correct.
And I'm going to leave like 10 minutes for questions. I think that's nice. So I have 9 minutes left. Okay, so I'm going to just spend 8 minutes on another application that, even though my talk is about chemistry, I want to emphasize, because I think many of us should start thinking about what are the best quantum advantage applications. And we argue in my group that quantum computer-aided design will be one. So let me just tell you what quantum computer-aided design is briefly. Okay, so we got already achieved supremacy, as mentioned by Frank, and supremacy is great. I mean, Sycamore really and the IBM chips really enter a new era where this is going to be more and more important. But we really haven't used them for an application yet. And I really don't want to underemphasize that. Of course, there's a lot of worldwide competition. The European groups, some very well exemplified by Frank, shouldn't be discounted, and Open Super Quantum Q or whatever it is, that project, and all the projects in Europe could be making big surprises. IQM, for example, and the Chinese groups as well. For example, here we see their quantum optical machines also have achieved supremacy. So why is this important? Because if you really think about it from the quantum simulation perspective, that means that particular device is unsimulable, the device itself. And therefore, it gave me the idea that pass the soccer ball to Tiha Kiao to actually make happen when he joined the group, was how can we make it sure that we can simulate those devices for design, okay? Because if you really want to just simulate a device, I argue we are already, of course, beyond capabilities, right? IBM Summit cannot simulate the actual raw device. So if you want to simulate and iterate and understand the noise and understand the design parameters for a real superconducting device, now you can only simulate subsystems. So you might need, for the same reason that you needed quantum simulation for chemistry, a quantum computer to simulate the superconducting device itself. So this is where we came in and said, what would it take to simulate, say, transmons? But obviously, you could also do this for quantum optical setups. You could do this for ion traps. The exercise will be the same. Will be take the Hamiltonian that you care about, map it to a spin 1/2 representation, truncate it the right way, use all the variational quantum eigensolver tricks that we can, or excited state variational eigensolver, or trotterization, and where do you land? And turns out you land roughly, or at least for us in terms of transmons, at 4 data qubits, okay? So basically, you need only 16 levels to simulate a transmon Hamiltonian for the energy ranges that we care about here. Arguably, say somebody, an expert like Frank, might say, oh my God, that's not really the case. Well, it's okay, Frank, we'll add an extra data qubit. Okay, so you know what I'm saying. This is log to the number of levels. So assuming it's 4, which we believe in our paper is the right number, means that, if you extrapolate in our plot here, somewhere in the next year or two, you will be able to simulate with a quantum computer, another quantum computer, better than a classical computer. What I mean by that is like subsystems that you cannot simulate classically. That's pretty deep, guys, because this might be the killer app. That's what I'm thinking. Okay, so I argue that, this is the main punchline of the second part of the talk. Future quantum computers need to be designed with the aid of existing quantum computers. Okay, so talk about Russian dolls. So, okay, so how do you do that? Well, there's a lot of technical things that in 8 minutes I won't be able to get into. Just to give you the overview, we need to encode the Hamiltonian into Pauli strings, then unleash the power of variational algorithms and Suzuki-Trotter. And this is how it works, right? So if you want to think about how to convert operators, one of the papers that Nico Sawaya at Intel collaborated with us, basically, led, and we collaborated with him. That's what I want to say, sorry. Is this idea of encoding the Hamiltonians into gray codes. Okay, so one interesting encoding for bosonic Hamiltonians, or this type of multi-level Hamiltonians, will be a gray code Hamiltonian rather than standard binary. So that's one of the kind of more technical developments that are needed for this. And then you have to think about, and this is what Tija was working out, how to map these Hamiltonians that have this form, these cosines that depend on this flux, into this kind of digital form that can then be converted by the gray code into this compact set of C and X operators. Okay. Another example that you want to think about, this is where Hannah Singh, who just graduated in my lab, also with Tim Menke. Hannah and Tim worked on a lot of work on the ansatz set that you need to think about for physically simulating transmons. So Tim is an expert in experiment and theory of transmons, and Hannah has been thinking a lot about ansatz in my lab and in Zapata, and this is what came out of it. So you can find the ground state by BQE, determine excited states by variational quantum deflation. And if, for example, your goal was to try to get the spectrum of this particular flux qubit, then you will kind of scan, for example, the external flux and look at these avoided crossings and so on. And then the error that we believe, like the chemical accuracy, will be 10 megahertz. And you can see that our predicted simulations will be under that error. So that tells you that perhaps four levels is four qubits per qubit is the right level of compression that you need here. Okay, and really just to tell you how versatile this is, let's just imagine that you want to verify G-wave pan. Let's imagine you have a quantum computer in your house. You have a Google quantum computer and you want to use it to verify a quantum optics experiment. Or you want, perhaps what we're thinking with Mario Kren in my lab and Jacob, is actually more than anything, design new quantum optics experiments. So we argue that you might need to design them by using a digital machine, and therefore those prisms, mode shifters, phase shifters, spin splitters, etc., could be also mapped to circuits, and this is what we did in this paper. And here is, for example, a simulated boson sampling on a quantum computer, right? So this is not just a stunt here. It's something that I think is going to be very useful as you actually want to start hybridizing and thinking about how to simulate one machine with another. Okay, so QCAD can also be used for quantum optics experiments. I was going to tell you about Orchestra. Maybe 1 second on it. I still have time. Some people don't know really what Zapata computing is doing. And I really want to try to explain to people that, of course, we develop quantum algorithms, but there is a tool that is open to all the academics in this room, and happy to introduce you to the right people at Zapata. It's being unleashed this quarter massively. And it is a tool that allows you to calculate and run hundreds of thousands of calculations. And it doesn't matter if you use Penny Lane or if you use Tequila or Pike-Wheel. It doesn't matter what quantum chemistry packages you're using. What this allows you to do is to package them into this kind of like modules that we're making easier and easier to use, as to speak, that you can glue together to calculate, hundreds of thousands of calculations. Okay, and you can see them in Tableau here. And this is what Zapata has been using to work with their clients and with our clients. And this is why we want to give it to the academic community. This is another tool that I think will unleash our productivity. Now, I want to go to I'm going to skip a lot of experiments here and go to this paper by Zapata. Okay, this is our unleashed collaboration of them with the research team there. I mean, I was not involved in this direct work. Jonathan Romero was leading this with Jérôme Gontier. And what is very interesting about this paper, I think, is that you take a look at molecules like propene or propine at the levels that British Petroleum needs, basically combustion level accuracy. And they conclude that the number of qubits required is 13 times the number of electrons. And here is the number of days that they estimate one of these simple molecules to take in a quantum computer. Okay? So it's pretty daunting and pretty despairing. And this just appeared actually in December. Well, remember what I told you about the modules? Well, there are two modules that just came out from my lab, paradoxically. I mean, even though I also am connected to Zapata, that could help you. One of them is the gradients module that Jacob and Abhinav developed, and the other one is the multi-resolution analysis BQE. So we reached out to Zapata, and we're in the process of trying to redo these calculations. We just started discussing with Zapata, but this is an example where this paper will be perhaps obsolete by the next year. But this paper is a very good example of the challenges of what BQE really requires, even by combining these new approaches. So I really recommend the community to start thinking about benchmarks together. So I want to skip a lot of this and just end with this very promising milestone/roadmap from IBM. If this is really going to happen, and we're going to have by 2023 1,000 qubits available on the cloud, I think the future for BQE and the future for chemistry is bright. And with that, I'm going to show a Zoom-like picture of my research group. I really cannot emphasize the work of all the group members under COVID. And I am ready to answer questions. And for that, I'm going to actually unmute my screen so we can see each other. We can see each other actually, face to face. So let me just stop presenting and happy to answer any questions.
All right. So I'm looking in the Slack right now. I guess let's go with maybe a question from Luke first.
Okay. Thanks, Alan. Great talk. I had a question. I mean, what always bothers me is the slow convergence with single particle basis. And you mentioned PNOs. I mean, something you could also use in addition is to have the F12, so the two-particle dependent data sets. Can you say a bit on how much you have integrated this or want to integrate that in your software stack?
I would love if you guys have some progress there or anybody has progress there in this room, we will definitely work to combine the F12. I come from I did my PhD in quantum Monte Carlo, so I was doing Jastros from 1999 to 2004. They were my thing. So when F12 came out, and I was so excited. So yes, I think that's a natural thing to add, Luke, and I think I would love to collaborate with anybody. And I know there's a couple papers already out there with F12. Yeah. We could put it together happily with whoever if you want to work with us on that.
Yeah, there was already a response on the chat on a paper from IBM, and I think that the challenge is really to combine everything together that make it accessible to everybody.
We're trying hard. We're trying hard in Tequila, and we are long overdue. I announced it when I announced Tequila. We're going to have a workshop, so maybe we can have an online workshop just in Tequila that is mostly workshop/hackathon, where we can get together and we help you implement whatever, everybody. But yes, maybe by 2022, hopefully we have F12 there and we lower again. So look, very good idea. F12, better gradients, better PNOs, and then the Zapata benchmark will keep lowering and lowering and lowering. And that I think that should be kind of like what the community could aim for, or at least our group and others, whoever wants to join us in that mission.
Okay.
Thanks for the question, Luke. I guess Barbara had a question which has been answered a little bit in the Slack, but maybe it bears a bit more discussion in here as well, given this is supposed to be one of the intro talks.
Okay, Barbara.
Barbara, do you want to ask?
I'm not looking at the Slack, unfortunately, because I'm speaking. But...
Oh, sorry, Barbara, you're muted. Well, you're not connected to the You're not connected to the.
Sorry, Barbara, I can't hear you.
You're not connected to the. Your audio doesn't seem to be coming through for some reason. All right. I might ask a question just to speed things along. Sorry. So Barbara asked, "What is multi-resolution analysis? Do you choose optimal orbitals, and how do you do that?"
Good question, Barbara. Let me explain. Sorry, I don't have slides for it, so I'll use my hands. So people traditionally, and by the way, we have Stephen White here in the room, which has done incredible work in that regard as well. Okay, with his wavelets as well. So there's many approaches about this, but the idea is, can you rethink any of the basis set? I mean, the basis set that we think about usually is a linear combination of Gaussian orbit functions. It has many problems. For example, the tails, overlap with each other quite a lot. So imagine that instead of that, you write a code that is based on the traditional multi-resolution grid type approaches where, if you want to describe a function in real space, you just add elements in the right places where it's changing very rapidly. And the Madness code by Harrison is one of the pioneering codes where you use such a basis numerically in a classical computer. Okay, so even if you were to use just the basis in the mean field, you get a lot of advantages, and it's optimized for the problem at hand because it's not a fixed basis like the Gaussian basis. Okay, then what this PNO is you do a low-cost correlated method on it and try to find out what is the best basis for correlation, and this is called pair natural orbital theory, and then you use that basis as your single particle basis where you start the quantum chemistry. In other words, you use a lot of classical numerics that comes from the field of differential equations, right? And again, you could also use real space Gauss, wavelets and other different approaches that Steven and Garnet-Chan and others have shown are also very efficient. So the MIVQE is just more a tool that came from the quantum chemistry development community, but there's others that come from the many-body community as well.
Thanks, Alan. It's a really great answer. Looking through the chat, I guess, Javi, I think you've got a question as well.
Yeah, I mean, if I can.
Please.
Yeah, hello, Alan. Thanks for the nice talk. So my question is about this MetaVQE, because you show a plot where you use this H4 in square configuration, and then you say, well, if I finish my MetaVQE and then re-optimize everything, I get slightly better. My question is, if you, instead of doing the MetaVQE and then re-optimize, if you do standard VQE and then taking the optimal parameters and do another VQE, would you lose? Would you gain? I mean, because re-optimizing the MetaVQE will have a cost. Can you use this cost as concatenate into standard VQEs? And just,
no, it's a little bit different, Javi. I think what is nice about the MetaVQE is that it gives you a very good starting point that is actually informed by the neighboring sites. Let's just imagine that you're going towards the phase transition, right? A bond breaking, or a bond rearrangement is like a mini phase transition too, right? Like the wave function has two different characters on the two sides, right?
Sure.
So you're coming in with a MetaVQE, you have this encoding layer that learns from kind of that behavior globally,
okay,
and gives you a starting point, right? And then from that starting point, then you relax the parameters and you do better, right? So arguably, it's learning more globally. You could potentially compare it more fairly to BQE circuits where you have the same number of parameters, okay?
sure.
And then you see which one does better, but I argue that the latter will get lost easier. And as you know, sometimes here it's not only it's also how easy you get to the minimum, because every optimization step is hundreds of thousands of measurements potentially, right, in your classical computer. So you really want to start as close as possible to the right answer.
Sure. Yeah. Well, that kind of answers my question. It's true that you have to compare with a circuit with the same number of parameters because MetaVQE has additional knowledge that you don't encode.
If you're already going to learn a wave function over a parameter set, say you have a Hobart model and you're changing, the ratio of correlation versus hopping, or you want to do, single-side energies versus hopping, things like that, you might as well do this. That's my point. Because you're going to be running many VQAs at once, well, run them in a meta sense. Run them all together. That's kind of the lesson from this paper.
Sure. Thanks.
Thanks, Javi, for the question. I have maybe a provocative question for you, Ilan. You've presented a lot of work today on looking at VQEs and thinking about, like quantum computing in the near term. Can you think of, I guess, a lot of the research we've seen so far from the chemistry side, where people have scoped out beyond classical algorithms and things that we would potentially use a quantum computer for, they implicitly work within fault tolerance. Can you think of anything that might make a chemistry problem particularly well suited to a near-term class, like a near-term algorithm, as opposed to a fault-tolerant algorithm?
Tom, your question is, I don't understand your question, because the whole point of the VQA is to try to be near term, right?
Right. So I'm saying, can you think of anything that might make like a chemistry problem more suited to being solved by a VQE rather than by, say, phase estimation?
Well, phase estimation and or all the long-term algorithms that, by the way, Nathan, I see his face right now, my new colleague at the University of Toronto, by the way, I'm so glad. We haven't interacted because of COVID too much, but look, we're looking like each other more and more, Nathan and I. Nathan has done fantastic work on those longer-term algorithms, right? That are way better because they will get the ground state, right? Like if you have a good approximation, they will get the ground state. Whereas the VQE, a big important point to make is the VQE is an ansatz, right? It's going to get you closer to the ground state, but it's not the ground state, right? It's like, in some sense, it's like traditional quantum chemistry. So if you, Tom, you're asking how to bring back the cost of those latter algorithms and make them fit in the near-term quantum computer, I think there's a lot of work to be done. But maybe I'm not understanding your question, and maybe I will let.
I guess I was more thinking on the chemistry side or the molecule side or like the system side, kind of what properties of a quantum system might make them easier to be solved by a VQE, as opposed to like something I'd want to attack with phase estimation.
Okay. I think both of them will be used for the same thing. Okay. Mm-hmm. The way we think about it, in my opinion, is you have transition metals, very degenerate systems. You're dealing with excited states, which also have very, very, very close levels of energy, with the wave function delocalized over several states. So sorry, the wave function entangling several states, right? This is where the classical quantum chemistry methods seem to not work very well. The chromium dimer, right? Six tuple bonds, right? Radicals, very correlated polyaromatic hydrocarbons. These type of systems where the electrons are correlated in a very, very delicate way are the ones where you need to do the quantum computer. I mean, otherwise you might want to just run a DFT and maybe you're happy. DFT corrected with machine learning. So I think if you're asking from the chemistry perspective, which systems, I think the systems will be the same for the near-term algorithms and the long-term algorithms.